Hello and welcome. This is Caitlin. We're on the final practice exam. We're on the What's in the Box page, and we're going to get to it with some fun reactions. We're going to be filling in the product for this one here. These are the reagents for oxymercuration, and demercuration happens in there as well. Demerc. This is, ooh, that's an extra, whatever, demerc. This is a Markovnikov addition of water across an alkyne. I like for the alkyne reactions to go through and show the halfway point. So if you were to think about adding an OH group to the more substituted carbon, I don't like that line, and a hydrogen to the less substituted carbon, right? That's how water adds. You would lose one pi bond. You would still have a double bond, making sure that you keep 1, 2, 3, 4, 5 carbons. And you would have an OH group on that more substituted carbon and a double bond here. This is an enol. This is our first context for learning about keto-enol tautomerization, and this was addressed on page 1 in the context of the beginning of decarboxylation. The enol then goes through, once again, that tautomerization process. The net result is that that hydrogen is going to transfer to that carbon, and that's not exactly how it happens mechanistically. You can look on page 1 for how that works. Well, in the reverse, we're still going to have 5 carbons. Now, instead of having a carbon-carbon double bond, we're going to have a carbon-oxygen double bond, and that hydrogen is now right there. It's now a CH3 group. So there we have formation of a ketone. The next one is the anti-Markovnikov addition, of water. And because we have an aldehyde, we know that our starting material must have been an alkyne. So we're just going to make sure we have the correct number of carbons. There's 5 carbons here in the ring. We'll call that 6 and 7. So we have our 5-membered ring. 6, and then since we know once again it's going to be an alkyne, we should have just like a straight line here. We want to show proper bond angles, never zigzag, an sp hybridized atom. And that's our starting material. Our alcohol would initially go to here. I think this is helpful to do. Let's do it. The alcohol would initially go to the less substituted carbon. So you'd have a double bond here. Yeah, it'd probably be trans. And again, here we see the enol form, and then it tautomerizes to the aldehyde, right? This carbon here becomes an aldehyde. Next one is this guy here is an oxygen nucleophile. And then over here we have potassium iodide and DMSO. This is a polar aprotic solvent. This is important sometimes for substitution reactions, but here we want to focus on the fact that we have an iodine nucleophile. All right, so we start thinking about whether or not a substitution reaction can occur, and first thing you should notice is that we have a nucleophile reacting with a nucleophile. That's not really good. The only way that you could really get an OH group to react, to actually get it to react with something like an iodide, is if you had HI, for example, and this would actually protonate it. It would make it into this guy, which is now a really wonderful leaving group. So now it's an electrophile, and then it could go on over a step or two to make the iodide. But in this case, because this guy on its own is a really, really bad leaving group, nothing's going to happen in that situation. They're just going to kind of swim around in that DMSO, and you waste some money. Part D is a fun Diels-Alder reaction, and the template for a Diels-Alder reaction is when you have a conjugated diene that matches up with a dienophile, and usually that dienophile has an electron withdrawing group. Now you may notice that the dienophile that I drew has a double bond, whereas the dienophile in our example has a triple bond. So we'll take that into account when we get to our example, but I like showing little templates. Put these guys together. This is the cycloaddition reaction. As a little transition state. So those electrons just kind of swim around. Remember, arrow pushing isn't super appropriate for Diels-Alder reactions. Oh, pardon me. That should be now a single bond here. We form 2 new carbon-carbon sigma bonds. And these 4 carbons from the diene are now connected, and we have a double bond in between these 2 carbons that were the dienophile. And like I said, arrow pushing isn't appropriate because it is a concerted mechanism, but whatever, it helps. So this is how we can explain and help us remember how we get that cyclohexene type product. So we know that in some way, shape, or form, our product is going to have a cyclohexene in it. As you can see, that our starting materials are a bit more complex than what we had initially. Initially in our sample, we had an alkene, but here we have an alkyne. So the way I think about it is we have an extra pi bond. So that means that another pi bond came along for the ride. We also have these 2 groups that are connected to these carbons. These are 2 ester groups. So we make sure that these guys come along for the ride as well. Okay. And then the only other little change between the diene that I gave as a sample and the diene that's given is just this methyl group on the second carbon. And that's really all there is to it. Oops, in the beginning, I should have given, since it's always, Diels-Alder reactions always give some kind of cyclohexene derivative, I should have started with that. And that's the product of that Diels-Alder reaction. Part E includes a Grignard reaction reagent here, which means that has a negative charge. We're going to look and see what are the differences between our product and our starting material. We notice that we have 4 carbons here that came from that Grignard. Since we had that negative charge there, we identified this as a carbon nucleophile. The rest of the stuff, these remaining 2 carbons, must have come from an electrophile. And the only carbon electrophile that you really know about is an alkyl halide. Alkyl bromides are best, but it could be a chloride or an iodide. And we want to add just a 2-carbon alkyl halide, and the primary helps because this actually is a SN2 reaction. The next one below, we are making an alcohol into an ether, and we note again that this is an oxygen nucleophile. We take a look at the new stuff. We see that we have a new oxygen-carbon bond. We know that the oxygen came from the nucleophile, so that must mean that the carbon came from the electrophile. And once again, really nice carbon electrophile is an alkyl halide. So we're just going to take that 1 carbon, just a methyl group, tack a halide on it. So you put in methyl bromide and you end up with your product. One thing you might be curious about is where that hydrogen went. The bromine actually went ahead and took off that. So the byproduct is not shown, but you would have HBr as a byproduct. That is page, whatever it was, sure, 3. And I hope you enjoyed. We'll see you on the next page.